You know, the electricity coming out of your wall outlet, it's not just a simple, steady stream. It's got this hidden rhythm, a very specific shape that honestly powers our entire modern world. So in this explainer, we're going to pull that shape apart and really understand it, the AC waveform.
Here's our roadmap. First, we'll cover the big question. What even is alternating current? Then we'll actually look at its shape. After that, we're going to get into how to measure its key features, and finally, we'll connect it all back to the real world and see why this actually matters for the power you use every day.
Visit youtube.com/avidsystem and don't forget to subscribe.
All right, let's jump right into section 1. What is alternating current? The best way to think about it is like the constant ebb and flow of power.
I want you to imagine electricity that doesn't just flow, it pulses. It rushes forward, stops, instantly flips around, rushes backward, stops, and then does that whole thing all over again dozens of times every single second. That constant change of direction, well, that's the big idea behind alternating current.
And it really clicks when you see it next to direct current, or DC. DC is super simple. It flows in one steady direction, kind of like water from a hose. Think of a battery. But AC, the stuff from our outlets, is constantly alternating its direction. It's a completely different beast.
So if this current is always changing, what does that even look like? How do you draw that? Well, that brings us right to section 2, the shape of AC and something called the sinusoidal waveform. This right here, this smooth, elegant, flowing curve, this is the sine wave. It's the purest, most perfect picture of alternating current. It's the signature of that back and forth motion we were just talking about.
But you know, the sine wave isn't just some abstract idea from a math textbook. It's the direct result of how we generate most of our power. It is the natural shape that gets created when a generator's coil spins inside a magnetic field. So the physics of how we make electricity is literally drawn out for us in this perfect repeating shape.
Okay, so we've got our shape. Now, let's learn how to read it. In section 3, we're going to check the wave's vital signs. Think of it like we're learning the anatomy of this electrical heartbeat.
First up is the period, which we represent with a capital T. This is just a measure of time. We're asking how long, in seconds, does it take for this wave to complete one full pattern? You know, to go from 0 up to its positive peak, down through 0 to its negative peak, and all the way back to 0 again. That length of time, that's the period.
Now, if the period tells us how long one cycle takes, frequency asks a different question. How many of these full cycles can we cram into 1 second? We measure this in a unit you've probably heard of before, Hertz, or Hz for short.
And here's the thing, period and frequency are basically two sides of the same coin. They have this really simple inverse relationship. So if you know one, you can always figure out the other. A wave with a really short period, for instance, is completing its cycles super fast, which means it has a high frequency. Makes sense, right?
And to make this totally real, the power coming from an outlet in North America has a frequency of 60 Hertz. That means the current is completing 60 full back-and-forth cycles every single second. Meanwhile, in Europe and a lot of the world, it's 50 Hertz. It's an unbelievably fast and precise rhythm that's happening all around us.
So the last vital sign we need to check is amplitude. If frequency is about how often the wave oscillates, amplitude is about how intense that oscillation is. It's the wave's maximum height, its peak value. We measure it in volts or amps, and simply put, a higher amplitude means more power.
All right, this brings us to our final section, and honestly, this might be the most important part. How do we take this constantly moving, abstract wave and boil it down to a single, useful number that tells us about its effective power?
So here's the puzzle. Since the wave is perfectly symmetrical, it spends half its time positive and the other half negative, its simple mathematical average is, well, it's 0. A voltage of 0 isn't very useful, is it? It's clearly doing work, so we need a much smarter way to measure its value.
And that smarter way is called the RMS value, which stands for root mean squared. The best way to think about it is as the effective value. It answers this question: what DC voltage would give you the exact same amount of power, the same heating effect, as this constantly changing AC waveform? It's what we call the work-doing equivalent.
And the great news is, converting between the peak value of the wave, its amplitude, and this useful RMS value is super straightforward. The RMS value is always about 70.7% of the peak, and the peak is about 1.414 times bigger than the RMS value.
And this leads to a pretty cool, mind-blowing fact. That 120 volts that you always associate with a wall outlet, guess what? That's the RMS value. That's the effective value. The actual peak voltage of that sine wave is spiking all the way up to almost 170 volts, 60 times every second.
So, let's just do a quick recap. The big takeaways are, AC reverses direction, DC doesn't. The pure shape of AC is the sine wave. Frequency, in hertz, tells us how often it cycles. Amplitude is its peak strength. And most importantly, the RMS value is how we measure its real effective power.
We've spent this whole time looking at the perfect, clean sine wave that power companies work so hard to give us. But here's a final thought for you. What happens when that pure, perfect waveform goes inside your laptop or your phone and gets all chopped up and distorted by all the digital stuff going on in there? Well, that's where the story of power gets even more interesting.
Thanks for watching.